Hello, everyone. I'm Lori DeToro, Senior Communications Manager for Turntide Technologies. Thank you so much for joining us today to learn more about power generation and our axial flux motors and inverters. We are thrilled to have Head of Product for Power Electronics, Chris Pierce, and Applications Engineer Matt Lamb presenting for us this morning. Before we get started, we have some housekeeping tips to share. This presentation is being recorded and will be available on demand on the Current and Wave website. We will be taking questions at the end of the presentation as well. So please use the Q&A section to ask your questions anytime during the webinar, and we will answer as many as possible. Remember to use the Q&A and not the chat. Remember, this is a live event, so when we mess up, and we will, laugh along with us. And that's it for housekeeping. We're ready to get started. Chris, please tell us a little bit about yourself, and you guys take it away.
Thanks very much, Laurie. My name's Chris Pierce. I'm Head of Product for Power Electronics here at Turntide. I've been with the business through Sevcon, Borg Warner, and now Turntide for 30 years, developing power electronics. My main interests are controls, firmware, systems, and functional safety. So it's good to see you all, and looking forward to this webinar.
And hi, my name is Matthew Lamb. I'm an applications engineer here at Turntide. I've been with the business for about 13 years now, also as part of the Avid Technologies group. And my background's in power electronics design and motor design. I've also done a stint in product testing and certification. And I've also got a keen interest in sustainability and recently completed a degree in that area. And I'm really looking forward to talking to you about this topic, power generation using axial flux motors and flexible power electronics. So I'm going to start off by just explaining a little bit about why now and why this topic is currently matters currently. And one of the things that we've seen as a business is economic factors driven largely by the geopolitical climate. But there's a big increase in customers that are looking at higher fuel efficiencies, and they've also got more compact space claims. And that creates a lot of challenges in terms of getting the products into those areas, and also hitting the required efficiency points at the operation points. They also are using, there's a wide range of applications that are coming through, and there's a huge that brings with it very demanding and requirements, particularly from an off-highway or marine environment, and there's also the renewable energy space as well. So there's a few drivers on those two fronts. And Chris, would you be able to give us some background on the inverter?
So one of the great benefits of the state of power electronics today is the capability to drive motors at key operating points of efficiency and control all of the elements of a generator train using power electronics, which when combined with axial flux motors to deliver high efficiency power conversion, it allows a flexible generation platform that can utilize both really highly efficient power electronics in conjunction with efficient motors to provide an optimally efficient generator system. So these are some of the topics we're gonna walk you through today, where conventional generators work and how they are constructed, and what we see the future possibilities with using our advanced AF motor and power electronics. So the generator design challenge, as it would be, is we need to produce power from either a battery or a internal combustion engine. We want to generate power. We want it in a small form factor. We have a problem to solve, which requires us to engineer a solution. We could hire a diesel generator, or we can come up with a much more flexible and bespoke design system which satisfies the cost we're trying to meet, the overall total cost of ownership, and satisfies the end use case within the space constraints that we have. So we have internal combustion engines that we can interface to our Axial Flux machines. The Axial Flux design interfaces to a wide range of commercially available generator applications, and with the right power electronics we can solve a multitude of generating and drive applications.
Thanks, Chris. Now, before we go on to some of the more technical details, I wanted to go through a little bit, explain a little bit about the difference between motoring and generating. Now, in the applications role, when I'm engaging with customers, this is a question that is commonly given to us and we commonly receive. So I just want to go over this at a very high level. And I think the best way to explain this is to look at power flow. So if we start off with motoring, and we're looking at we have an electrical power source, that might be a battery, it can be another generator system, but that then goes into what's called the DC link, or the DC link voltage bus, and that supplies the inverter, and the power moves from the DC link through the inverter into the motor, and the inverter then drives the motor, and what you get out is mechanical power, and that's useful mechanical power that's the output of this system. And then if we look at the generating, again, the basic generating power flow, and I'm going to start off with more conventional generators. You have effectively the mechanical input, so everything is going in reverse. You have the mechanical power as the input, and that goes back into in this case, more conventional topology. You've got the AC generator that then produces an AC supply, and that then goes into the electrical power sink in whatever form that may be. For more modern systems which have a more optimized generating topology, again, you've got the same mechanical power input, that then goes into the motor or generator, and you will have either in the power electronics area, you'll have either an active rectifier inverter or a synchronous rectifier, and that then goes into the DC link and then goes back into the electrical power sink. So again, that could be a battery, for example. And then Chris, could you talk through the next slide, please?
Sure. So here's a conventional anatomy of a typical commercial grade generator that you might hire from anyone in the local Yellow Pages, and within that system are some very basic generator functions, and this is commonly what we think of as a generator or a genset. This is an internal combustion engine, diesel engine, using usually an excited rotor generator, which produces directly AC three-phase mains out to a connector, big blue round connector that you will plug in a load, and effectively that looks like any AC supply, domestic supply that you'll see, and you can plug in any appropriate load to that. There are lots of reasons why this is a very effective and common approach. it's very simple. The diesel engine just runs at a fixed 1500 RPM or 1800 RPM, and that is directly related to the three-phase supply that comes out of that generator. That runs at a fixed frequency of AC of a 50 hertz AC or 60 hertz AC at 415 volts here in the UK, or whatever your variation is around the world. And this is a very standard architecture, and this often leads to a bit of confusion when we talk about more optimized approaches, because this really is a direct AC feed system. There's a direct online start that creates a large inrush current unless we insert a soft start piece of electronics here, which kind of chops the voltage down but doesn't do anything with the frequency. This is a direct online start AC induction machine connected to a pump, a water pump in this case. It's just the task at hand is to drive water through the pump. We're going to use this AC induction machine to drive the pump, and we're just going to plug it into this conventional generator. This works. It's one size fits everything. It is a very, very cost sensitive market, and it is designed to be as universal and as cheap as possible, not to be as optimized as possible. The engine is not optimized to work at its most efficient point, and there is no consideration on optimizing output loads to operate in their most efficient point. The load motor, in this case, an AC induction machine, has peak operating point, and the pump has also operating efficiency. In this kind of situation, if we wanted to control the flow of water through this pump, the only way to effectively do that is to shut off the flow and increase the back pressure, which effectively slows the pump down, but the load on the internal combustion engine remains the same. Then generator load comes down, and it's just not a very efficient way to operate this if you're not doing anything but maximum load. So next slide, please, Matt. So in our optimized approach, we would recommend that using an axial flux machine attached to our internal combustion engine, as well as power electronics to control that axial flux machine, you can decouple the relationship between the engine speed and the load speed. So now in our example here, we have axial flux machine connected to the internal combustion engine connected to an inverter. This inverter creates and controls a common DC link. In this case, it would be 400 volts for this type of inverter. This is then consumed by another inverter connected to our load. So this three-phase output from this inverter would be a variable frequency, variable voltage, completely decoupled from the internal combustion engine speed, which is optimized to operate the pump at any speed, and critically the most efficient best efficient point for the work to be done. So critical parameters here are the fuel consumption of the diesel engine and the best efficient point of the pump. We can now control both of these elements independently from each other, where previously they were linked by the common standard mains frequency. We can now throttle this pump with a power electronics dedicated to controlling the load, and we created a very flexible platform solution which we can optimize total cost of ownership and minimize the amount of hydrocarbons consumed or whatever alternative fuel in our internal combustion engine we're using. And we are also optimizing the system for power factor and waveforming and shaping of the pump's load currents to maintain optimal efficiency throughout the whole system. And doing this, we can create large benefits in the total cost of ownership for any load which is operating away from its maximum operating point. If both systems, both conventional and optimized systems, are always only ever running at maximum conversion, power conversion, absolutely flat out, then the total cost of ownership is about the same. In the situation where we are controlling the load more effectively and efficiently, then we have got clear total cost of ownership advantages. Next slide, please, Matt. So just running through the points that we've just covered here, the fixed speed synchronous generators have very limited controllability of the output parameters. So in the optimized approach, we can control DC link voltage and the internal combustion engine's optimal speed. We've got a larger footprint in a conventional system due to typically radial flux, separately excited rotor AC generators. We have a slower response time from the engine, so large dynamic load changes on the output cause the generator to have to respond dynamically to meet that load, and that can be quite a slow response compared to an optimized power electronics inverter based solution, which can respond much faster whilst the engine catches up. And obviously fuel consumption we've discussed at partial loads can be massively reduced by keeping the generator operating at its peak operating efficiency for fuel consumption rather than idling it down. Next slide, please, Matt. So the key takeaways then are the power density of axial flux motors give us a substantial power density advantage. The power electronics give us an advanced flexibility over the dynamic response of the control and efficiency. Total cost of ownership is the key metric of the right architecture, and using an inverter-based active control of the generator system means that we have a much more optimized system. That said, the optimized system does need to, the application should be matched to the architecture. As I say, if you're only ever using the system at 100% load, then the trade-off is slightly tilted towards a completely passive conversion. But that's a fairly rare and unique application that only ever works at 100% load. Thanks, Matt.
Thank you very much. Thanks, Chris. So I'm going to we're going to break this down now. We've talked about the overall systems there, and the overall system required for the generators. And we're going to break this down into individual components now. And I'm going to talk about the axial flux motors and why these are so good. What makes them different? What makes them better? And the high torque density is a key thing that's been talked about, and that comes from the shape of the motor. So axial flux motors, they generally have a wider diameter and a shorter length compared to radial flux machines, and hence they're often referred to as pancake motors. The thing that the high torque is gained from the size of the rotor, and also the magnetic flux path, because there is more magnet in the diameter, in the wider diameter of the rotor, and so that then is able to give lower core losses. It improves the efficiency, and also, as I said, it increases the torque density. The short length of the motor allows it to fit in some quite tight spaces. I think particularly when we're looking at internal combustion engines and gearboxes, the difference, the length that where you're able to fit a motor in without remodifying a whole other parts of the architecture. The size you have to be able to fit in there, the space claim, is actually quite small, and that's we found that the Axial Flux machines are able to fit in those spaces quite well. There's a modular design, so our particular Axial Flux motors have been designed with a modular approach. So if you want to stack the motors to get more power, you can do so. And there's also other flexible integration options that we have available as well in terms of orientation of the top box, of the coolant ports, and also the through shaft for the motor allows you to drive other auxiliaries. Say if you have if you have an internal combustion engine that's going into a generator and then has other auxiliaries on the back of that, you're able to put the shaft through there. So we found that that's become very popular. And I think the other thing is the wide range of applications, and we've mentioned before about the standards that come with that, and the robust design, the IP capabilities, they have all come to the fore, and we found that the Axial Flux machines are performing much better in those areas. Yeah, just again to review that. So more Newton meters per kilogram effectively because of the torque density. This is particularly useful for lower speed applications. So our AF 430 motor, that's been specifically designed for use with diesel internal combustion engines or ICE engines. Not to say that they're solely used with diesel. We've found applications which use them with petrol and other fuels as well. So yeah, they are definitely working in that space. And the higher efficiency, as we've talked about, the reduced electromagnetic losses, and also the ability to modify, so to have different turn counts of the motor and allow the motors to be optimized for a particular operating point or operating speed. And that's something that we always work very closely with our customers to obtain. And then also the system integration. So we're able to pair these directly with the inverters, and we have many inverters that the Axial Flux machines are paired with. And also the flexibility in terms of the integration with the rest of the system, be it the cooling hoses for the coolant system. It uses WEG as opposed to another type of coolant, so that allows easier integration with common systems that we find in particularly in the automotive, but in other industries and applications as well. And yeah, like I said before about the top box and how we're able to change the orientation of that and the through shaft. Chris, could you talk more about the inverters, please?
Sure. So we talked about the power electronics in power generation and power conversion. So this would directly connect to the AF motor attached to the generator, and the output of this system would be a DC link voltage to supply the DC link. So the first generator inverter is responsible for the generation and control of the DC link, and then subsequent inverters can be connected to this DC supply, which then can be converted back into multiple AC loads, which can be doing multiple tasks, such as traction pumps off the same DC link supply. So obviously the inverters we choose must be rated for the DC link voltage, and the DC link voltage that we select dictates the peak power point of the overall system, and has to be rated for the inverters to operate to. So there'll be a minimum maximum voltage range of the DC link that is acceptable within the generator system, and the DC link will be regulated to be within that range by the generator controlling inverter. The current within the generator to produce the DC link power needs to be rated to the motor. So the current in the motor converting the power in the engine and delivering that through to the DC link has to be rated, and the peak and continuous load of this generator system needs to be understood, such that the thermal capacity of the generator motor and the generator inverter are such that thermal constraints do not prevent the system from delivering its intended function, as is true of the output inverters, and obviously the overall power consumption on the outputs needs to be matched to the power consumption of or power production of the prime mover and generator. So the DC link control is interesting, as this is the primary source of energy for the whole generator, whatever that energy is being used for, whether it is to create AC via a grid-tied inverter producing 415 mains, or the inverters attached to a traction load to move this generator system around, or pump systems attached to the DC link to control other hydraulic systems or whatever. So the DC link we're going to talk about a little bit more, and the inverter configuration is what is the key to optimizing the overall system optimization. Next slide, please, Matt. So the DC link is a central part of the overall optimized generator system, as this is a staging post which allows us to decouple the engine peak efficiency operating point and the generating motor peak efficiency operating point. Those two efficiencies are multiplied together to be optimal, to produce power at that optimal point, regardless of what the loads are doing. However, the DC link, the inverters have DC links within them. However, this can be added to with an additional capacitance, either a supercapacitor or conventional capacitors, to actually increase the overall DC link to absorb large load transients on the output, and those load transients can absorb a lot more power out than the generator is supplying at an instantaneous point, and that duration of that overload capacity is dictated by the attached DC link. So within that DC link capacity, we are doing a number of things. The smaller that DC link, so if there's no additional capacity and we are tying all of the inverters together with no additional DC link capacitance, then the transient response of the voltage control is critical, and the stability of that DC link is substantially more challenging than if it is a large DC link supply. Additionally, we can use a battery in that position of the DC link also to buffer and supply surge power, and also provide standby power if we don't wish to run the internal combustion engine as well. Maintaining that DC bus voltage to a known voltage provides a stable platform for the loads to operate from. And in larger DC bus microgrid type systems, there is a separation between that DC bus and the generator supply. But in this example, we're assuming that a DC bus is controlled entirely by the generator system, and that DC bus is then supplied to the dynamic loads via other inverters attached to that DC link. So they are running off a supply which is stable and doesn't collapse under transient loads. That all needs to be determined in terms of the intended function and what it is we're actually trying to drive. Once we've got this system designed in terms of load output surge capacity, input continuous generation, diesel engine control of speed, and DC link control of voltage, we can then orchestrate all of those things together via a centralized control system, which allows us to optimize that system for all of the use cases that we're planning for. Next slide, please, Matt. Can you go to the next slide, please, Matt?
It should be on there.
Oh, sorry, my mistake. Drifted off because it was the same. We should have had more pictures.
Yes.
So obviously talking about coordinated control. So the engine itself has a speed setting based on the throttle position. We want to maintain that at the most fuel efficient point for the system. That is a fairly slow time constant changing thing. The generator control will at sample rate at time constants of the motor change the load on the diesel engine to maintain the DC link voltage at a constant level, and overall the output loads will pull power from the DC link, causing that DC link to sag a bit, which will cause the generator controller to put power into the DC link, which will pull power from the generator, loading up the diesel engine, which then will also govern up to the target optimal speed. So there's some really interesting control aspects to this kind of generator system. It's very flexible, and we can predict quite well the overall efficiency and fuel optimization and alternative fuel. So we can also, via the DC link, bring in alternative sources of power through DC-DC converters from wind and solar converters, so that the overall system is completely flexible. Thanks, Matt. So some of the trade-offs of the design choices we have for this inverter, this inverter-based generator. I mean, nobody is suggesting that we're looking to displace the conventional genset option, which anybody can go and hire and fill with fuel and run to do whatever function you require. You may well have to oversize that generator for if you want to run a 50 kilowatt pump. You probably have to hire a 70 kilowatt generator in order to cover the direct online start function of that motor, even with a soft start. It's not going to be running very efficiently, and you're not going to get the biggest bang for buck from your fuel supply, but it is a very cost-effective solution if you need a quick generator option. A synchronous rectifier. We haven't talked about synchronous rectifiers. This option does crop up whereby you create a DC link from your permanent magnet machine. It is more efficient than a diode rectifier. It is basically a diode rectifier which uses silicon MOSFETs, IGBTs to do the rectification instead of diodes. It's much more efficient. However, we have broken the optimized engine operating point function. So we now have to govern the DC link voltage via the generator speed and engine. So then we've lost that optimization, but we can still attach inverters to that and control output loads, but the DC fluctuation is much larger and may come down under load substantially without any optimized control of the generator system. Back-to-back inverter is going to give you full optimized control of both loads and generator functions. This will give you the absolute maximum optimization in terms of right sizing both generator and load inverters and pumps, and internal combustion engine size. That means that the engine size can be smaller, the fuel consumption will be less, the generator will run at its optimal efficiency, and the loads can be run at their optimal efficiency. So where the loads are dynamic and variable, and cost, space, and total cost of ownership are critical functions, then the full back-to-back inverter type solution gives us some clear benefits over our conventional or even semi power electronic clever options. Next slide, please, Matt. So to close then, the overall generator concept, we are thinking about how to manage diverse electrical demands and generation using under dynamic conditions, using the latest thinking in terms of power generation. It allows for smaller, more compact, more efficient and more flexible generating platforms. We can optimize load management across duty cycles to ensure maximized efficiency, and making the variable loads and demands that modern applications are seeing in terms of pumps and renewable and sustainable options of power generation, as well as uninterruptible supplies. We have a much more flexible and platform approach to the conventional power generation question. Some of the future facing ideas, with bidirectional energy flow in terms of grid tied systems, allow us to think about wider applications of generators and power storage as well. So these are all things we're thinking about now, and would be interested to hear about any future requirements or ideas that you're thinking of as well, which could utilize some of these ideas. So next slide, please, Matt.
Okay, thanks, Chris. Thank you very much for that. I'm going to just introduce or explain really the range of architectural options that we've witnessed as a business. and just sort of explain a little bit about why that's important, or the challenges that brings. So I think common applications in industries, we've talked about some of them during the presentation, but just to go over some of them again. So there's off-highway and agriculture, and I've lumped those together because they're often very similar in the architectural approach. There's also mobile electrical power generation, which we're seeing an increase of these applications coming through. There's general automotive, and that's often similar to off-highway and agriculture, but the powers and complexity seem to are often a little bit less. And then there's also, we've seen marine applications coming through, as well as the renewable energy sector. So there's obviously a diverse range of application in industries there, and each one of those comes with it, brings with it its own standards and also requirements from a both technical and business perspective. Looking at common generator inputs, I mean, we have internal combustion engines, which we've talked a lot about today. There's also renewably driven sources, which well, that can be a range of things from wind to marine, wave, turbines, currents. There's all sorts of different technologies that are coming out, organic fluids as well, that are coming out. And there is system braking. This is commonly seen in vehicles, or particularly like in the automotive sector, where you have the braking of a system, or even the rail sector as well, where that comes in as a part of a regeneration of a battery or electrical power area. I've also been in discussions with people who are using flywheels as an input, and also where the motor's being used as a starter, and that's to start the generator up, or to start an internal combustion engine up. Yeah, there's many different applications like that that are coming through. The connection types on the input, we've witnessed both hard mounting to a shaft, and by that I mean the shaft coming directly into the motor, and also pulley systems where the motor is placed to the side of the shaft or the generator. So both of those options we're seeing coming through. Then for the power buffer, there's a huge range of options here. Chris talked about some of them earlier on. There's batteries, there's supercapacitors, there's some applications just use the system component capacitance, so the capacitance of, say, just the inverters or other auxiliaries on the DC bus line. And there's external application capacitance, so ones where in the grid, for example, external parts of that system are being used as part of the power buffer. And then looking at mechanical buffers, I think one of the most common ones that I've come across is hydraulics, where hydraulic reservoirs used as a power buffer. And also, I think one of the new ones that's coming through is flywheels. Now, I mentioned that as both as an input, but it's also now seeing this being used as a power buffer to store energy for a period of time. And now, looking at the different control methodologies, I think there's a lot of innovation coming through here, and these are being developed all the time. And there's also new standards that are coming in, and new requirements which are making causing a lot of challenges, I would say, within the industry. But also, I think that brings with it a lot of opportunity for innovation and new and better control systems to come through. So from an inverter point of view, the main ones that are used are torque control, current control, and then voltage control. This can be done internally within an inverter or by an external ECU system. So a system that looks at the overall control of everything within the system itself. There's also a lot of cybersecurity. Undoubtedly, many of you will have come across the new standards that have been rolled out over the last 2 years, and that's adding extra complexity into these into the control methodologies and the way that interacts with other systems. And we have the battery charging as well, so commonly the BMS. And yeah, I mean, this is just a general taster of the options that are there. This isn't comprehensive. There are others that are out there, and I'm very sure that as the technology progresses as well and more options come through, that this is just going to expand even further. Now, designing for ruggedized operation or designing for extreme environments. So looking at the thermal management of the system, it's something that Chris talked about before in terms of the power electronics, and we see this as a critical part of the system. So our motors, if you look at the data sheets, are rated to the rating point is 55 degrees C coolant and 45 degrees C air, and motors are generally they are the output is dynamic depending upon the cooling temperature, the cooling system temperature, and so that is really important to be understood, and how the thermal management of the system will operate, and also what the with the extremes, how that will impact upon the motor performance, but also the power electronics performance. So it's really the system performance overall, and the coolant temperatures and the air temperatures do play and have a big play on that aspect of the system. Then if we look at shock and vibration, so again, when you were looking at a huge range of applications, you've got things from off-highway, which has a very stringent set of standards, looking at vibration and shock, and these can be very, very demanding. And then you also have marine, which has a separate set of standards to go with it, and then you also have rail and other automotive. So there's again a big range of standards, and making sure that the products are designed and tested to these standards and are able to pass these standards is very important part of the process, to make sure that the system, when it's released, is not only works, but it's durable and can continue to do so with the best efficiency points for throughout its lifetime, or the intended lifetime of the application. And again, another thing that we're seeing a lot of as well at the minute is IP rating, and I think that our products are generally IP67 and IP6K9K, so the highest level really of IP ratings, and that's against dust, moisture, and other contaminants. And we don't stop here, so we're continuously looking ahead. Hybrid systems are becoming more and more important. We're seeing that across our customer base, and also with different inquiries. And that axial flux motors, as I've said before, paired with the intelligent inverters, these can provide the huge system efficiencies, the best system efficiencies, and also are able to manage the loads, the dynamic requirements of the loads in the best way. And then we have the types of applications that I've just described before. There's a lot of remote applications. There's a lot of applications where the system is difficult to get to. So they need to be compact, they need to be reliable, and they need to be really efficient. And once they're in, they need to stay there, and they need to work. And this is this is across the different industries, renewable, marine, automotive, off-highway. Like I said before, there's those are big requirements in those areas, and we're looking at the how to make sure that our platforms are really easy to integrate, and the systems are plug and play. So you will get a system, it will be optimized, it will be ready, it will have been reviewed properly, and then you're able to plug this into your application and get it working as quickly as possible. So that reduces any downtime that you have, and it also increases the time that it available for testing and running the system. Finally, just to go look at the final set. Compact high efficiency generator architectures, they are continuing to expand into hybrid systems, remote power applications, and also we're looking at next generation distributed energy platforms to try and create the best products possible for our customers, and work with them to look at new areas for innovation where we can explore and move to create more efficient, higher efficiency products, and support all the challenges, help them with the challenges that they face. Thank you very much for listening. I'm going to pass on to Laurie now, who's going to ask us some questions, hopefully. I'm hoping.
We have a few minutes for some questions. Thank you both for the great presentation. It was awesome. I'm going to start with the first question, but attendees, as we're asking these, if you have other questions that come up, please let us know. I think you guys talked about this briefly during the presentation, but the first question is, what are the cooling requirements for the axial flux motors?
Yep, I can take this. So the cooling requirements are that it's WEG, 50-50 WEG, so ethylene glycol and water mix. That's basically it. So that's really commonly used in many different industries, and we've seen applications where I think commonly an application will plug the coolant into the inverter first, and then it will come from the inverter and then go into the motor. That's commonly, you can do it the other way around, but that's the most common way of doing it, to make sure the electronics are the coolest thing first, and then putting them into the coolant into the motor. You can also do it in a parallel methodology, but that tends to make you would need a manifold, and that tends to increase the complexity of the cooling circuit. I hope that answers your question.
I think it does. If it doesn't, you guys can let us know. The next one is, what are the key parameters for selecting the correct power electronics?
Chris, do you want to take that?
Good question, Laurie. Yeah, I'll take that. So when sizing the power electronics, the key questions are fundamentally about the overall DC link voltage range. It's critical that the voltage range on your DC link is rated to supply the loads in the correct way. If you're using a grid forming inverter, you're going to need to be at least above 650 volts to produce 415 volts reliably. You need to make sure that your inverters are capable of that, or if you're comfortable, or your loads only require 400 volts, that's another question. So that that needs to be specified and understood. The motor currents are critical to achieve the power points and the torques required to deliver the system powers, and of course the overall thermal rating of the system is governed by the continuous current rating of the system at the coolant temperature that you are running the system at. So there's a lot of interdependent parameters there. The heat rejection of the inverter and motor system, the continuous rating and duty cycle of the generator design, and obviously all interrelated to the currents and the voltages, and all ties back to the overall power output of the system we're designing.
Great, thank you. First, someone said thanks for all the great information, so that's always nice to hear. You were talking about cybersecurity. In what way is the motor connected, in air quotes? Can it be on or off? Question.
So the motor, in terms of cybersecurity, that's more a question for the system itself, and more related to the, I would say, the power electronics. The motor in itself is fairly dumb in that respect. It doesn't really integrate with the system from a cybersecurity level. Chris, I don't know, are you able to provide a bit more
that's
information
correct.
on?
So a motor in its own right isn't subject to cybersecurity regulation or compliance. It is the power electronics, which are the network connected power electronics, which are vulnerable to cyber attack and malicious actor intervention, which may lead to the motor misbehaving, turning off, disrupting, denial of service of that system. So that is where the cybersecurity is required, and that is in the the wirelessly connected system of our remote monitored generator system. That is vulnerable to cyber attacks. So that's where the protection would be. And our next generation of power electronics will be fully cyber secure, according to the CRA, the European Cyber Resilience Act, and UNEC Reg 155, as well as other more class 3 standards for cybersecurity. But we're starting to implement those important and critical infrastructure protections now.
Excellent. So we probably have time for maybe 2 more questions. The next one is, applying this motor in our situation, marine parallel hybrid propulsion, are we using a clutch, or what are the options?
I mean, you could use a clutch.
If it's, you don't need a clutch, because
No.
you can control the amount of load on the electrical system with the power electronics, such that it's like effectively an electronic clutch, whereby the and obviously I don't know what the system is, but it's when you have an axial flux machine on the bolted to the output bell housing of your diesel generator, you can drive through a hollow shaft of the machine. The electrical machine has a hollow shaft which will take a spline into a drive shaft, which sticks out of the back of the vessel and drives the propeller as normal. And in parallel to that, so that is a parallel hybrid architecture, you can then drive that shaft in. You can take power off that shaft to generate into batteries, for instance. If a clutch would make sense if you wanted stealth mode operation of the propeller, where you want to actually drive the propeller from that power electronics, which is entirely possible. So it's a bi-directional control through the same inverter. You could actually drive the propeller electrically, but you would really want to disconnect the diesel engine, because that would just load everything up. So yeah, but if you were just looking to generate off that power shaft, that propeller shaft, you wouldn't need to disconnect it. You could load it electronically or unload it electronically.
Excellent. Well, that is all we have time for today. Thanks so much for your questions. Chris and Matt, thank you so much for the great presentation. Lots of great information. Attendees, thank you for joining us as well. This webinar will be available on demand in about 48 hours, and we hope you all have a great week. Thanks so much.
Thank you very much.
Thanks very much, everybody.